Thank you, David. Thanks for inviting me. It's fun to be back. As you'll see, this is FWAM 7. So in other words, we've had sort of a algorithms and mathematics autumn meeting. It's had the, we started the first one 6 years ago. So I think it's going pretty well. And so I'm going to tell you some stuff about function approximation, almost entirely in one dimension, and a little bit of opinions about higher dimensions later. But there's so much fun stuff you can do in one dimension that you'll end up applying anyway that I think it's the right balance. So, OK, so I'm going to do a worked example. A lot of it is going to have little code snippets, and you don't have to write it all down because I'll put up code samples later. And they're in Julia, but that sort of doesn't matter, right? It doesn't matter what the language is. So what we're trying to do is approximate an expensive function by a cheap one. This is what people yesterday were calling a surrogate, or there was some other term that was even less common for me. Like a what? Emulator, thank you, yes. So if you like, we're going to spend a lot of time doing really good surrogates or emulators in one dimension. And then you can worry about high dimensions later. So the costly function is this. All right, here comes the pointer. Does a million operations, summing 1 over k from k is 1 to a million to the power x. So that just can be any expensive function you like. But this is just for the demo. OK, let's check that it evaluates something. It evaluates something. Those of you can think about that number if you want, but we'll talk about it later. And this little benchmarking thing just says it does some timings of the function, and it tells you it takes 20 milliseconds to evaluate. So that means if you want to even just plot the thing with 200 points, we're waiting 4 seconds, which is sort of annoying.
Alex?
Yes?
Could we possibly get your main screen? This is for the Zoom people, for the people on the AV. Get your screen on the side screens.
Sorry.
This isn't your.
Yeah, I don't know how to do that.
I just wanted to interrupt to ask for that.
OK. Thanks. OK. Yeah, you're going to want to read the code. OK, so we're going to want, and just to be concrete, we want this function between 1.1 and 5. So that's what that plot shows. It looks sort of well behaved, right? So let's choose some nodes, and these are x1 to xn, and we're going to evaluate that function at those nodes and see what we can do with those. So here's the data, if you like. I used equispaced nodes for now. So, and again, there's experts in the room, and they are going to have to hold their tongues and tell me, to resist telling me I'm doing it wrong. Because the point of this is actually to teach you all how to do this yourself. Because in 1D, you can do most things yourself, and there's no reason why you shouldn't. You can just write simple codes like this. OK, so 10 is the number of points. Here's the nodes. They go from 1.1 to 5. And here's evaluating our costly function at each of them. If you're not a Julia person, this dot just means apply it to each element of a vector. OK, so yeah, at the moment, we have the ability to choose the nodes, because we're building the surrogate. But later, you may have nodes forced upon you, and the rest of the talk will be of interest then. So f seems smooth, so let's try a polynomial interpolant. F tilde is going to be the interpolant, or the cheap approximant. So you sum up ck times x to the k. OK, we want to enforce that, matching the value, the data at each node. That's called an interpolant. It means you enforce the matching at a set of points. And so if we do that, oh, sorry, I seem to have missed off the c's here. There should be a ck there. You just write down f tilde equals fj. And another word for this is collocation. So, and there's one node. Each node gives you a row of a linear system. And so there's n nodes. There's n unknowns, which are the ck coefficients. So you get a square linear system involving a matrix which we'll call V, and that's because it's called a van der Maan matrix if you look in any numerical analysis book. It's easy to prove via its determinant that if the nodes are distinct, then it's non-singular, so you're going to, at least in exact arithmetic, you'll get a unique solution for this. All right, any questions about that? Okay, good. So here's your van der Maan matrix in LaTeX and in Julia printout. So you can see the first column is is all of the nodes to the power 0, so that's just 1. The second is to the power 1, to the power 2, and so on. Okay, so here's the van der Maan matrix, and you start to look at it, and you're like, well, these are of size sort of order 1, and here we're dealing with numbers of size 10 to the 6. So you're already like feeling a bit bad about this matrix. It's you shouldn't really work with things where the columns really differ massively in magnitude. So, okay. But let's go ahead. Remember, we're going to do naive things, and then we're going to slowly make it better. So backslash does whatever the linear algebra library is under the hood in your language. It'll be LU, pivoted LU or something. We don't have to worry about it, almost exactly what it's doing there. But you have to, we will discuss later the properties of sort of what you would like the answer to have. But this is the simplest way to get those coefficients. Write out the linear system and solve it in the computer. Okay, we're going to test this. You should always test your interpolant, so pick a point. Make sure it's not near any of the nodes. Here's your approximant now. This is what I called F tilde. You're going to sum up use the coefficients you have, sum the monomials. And notice, again, if you're not a Julia person, this is like a cute little way of writing a for loop and summing it in one line that is sort of Julian style. So, okay. And so now, subtract the approximant from what the true function is at that point. You get 0.02, and that's pretty terrible. So, okay. Is it cheap, at least? So, yes, you can evaluate this 1 billion times a second. Okay, so let's try that. Take this Julia function, right, that just did this little sum over these, this list, this variable length array, and test that, and it takes 1 microsecond. So that's 10,000 times faster than the original. And you're like, okay, well, that's good. But, maybe you want to actually do this thing as fast as possible, because this is some function that's going to be right inside the inner loop of your code. So you can, in Julia, you can pretty easily get to much better performance, mainly by using a good library implementation of summing the coefficients of a polynomial like that, or evaluating a polynomial. That's called eval poly. Put in 1.8. This little trick here is actually to, now you start getting into little HPC things, and many languages will have such tricks. It's to tell Julia that this thing is of a fixed length set of coefficients. And once it knows its fixed length, it can actually compile a custom evaluator for that length, which will use SIMD and various stuff. And then you get 2 nanoseconds per eval. So now that's actually pretty good. And if you are if you're Daria Malhotra or Marco Barboni or many of our other HPC experts, then you can get this down to 0.3 nanoseconds per eval for a sensible-sized polynomial like that. Okay, so it's cheap and wrong. Okay, so increase the node number. That's a good way to try and get it more accurate, right? Just use more data. I think this is what we were talking about yesterday. All right, so you've got to increase the number of nodes and therefore increase the degree of the polynomial because it's a square system, right? You're trying to interpolate. It's got to go through all of that data. And so what we're doing now, by the way, is first just going to plot what the difference between your approximant and the true function is on a fine grid to see whether you're picking an arbitrary test point was a good idea. Your arbitrary test point was here, And you can see actually the error is 10 times bigger over here. So that tells you that you can have very non-uniform error behavior. And so you should really do a uniform. So a word for that is to verify the uniform or maximum error. Sometimes it's called the L infinity error or just the soup norm error. There's a million ways of saying the worst case error. So let's bump up the number of nodes to 30. Okay, here it is. The error is 0 essentially at all of those nodes, and it's got a horrible spike here and a horrible spike here. These spikes are smaller than the original spike because we're using 3 times as many nodes, but it's still a pretty terrible, 0.004 is a pretty terrible error. And if you start cranking it up even higher, it gets worse. So you're in trouble. So now you have to start thinking. Okay. But what you should do as a numerical analyst is start investigating. Why is it going wrong? So let's just see what's happening at n as 40 nodes. And let's evaluate right near this nasty spike here at x is 5, which is, remember where the original function was the smoothest, over on the right-hand side. So it really should not be a troublesome area. So why on earth is it going wrong there? So take those numbers that were being summed in the approximant, right? ck x to the k minus 1 for k is 1 to n. Okay. Have a look at those numbers. Here's some of them. Minus 5 e to the 10, plus 4 e to the 10, 1.3 e to the 11. Okay. All of these numbers are adding up to give you an answer which is about size 1. So that's called catastrophic cancellation. And it's a huge warning sign that you're doing something unstable, and that, in fact, you can look at these numbers and show that and predict where the limit of accuracy you're going to get is, right? So if I look at these numbers, they're size 10 to the 11, and we're working in double precision, whose rounding error is 10 to the minus 16. So you'd now just compare these numbers. You're going to lose 11 digits. You started off with 16. So at best, you're going to get whatever the difference between those is. I actually meant 4, I guess. No, 5. Yeah, 16 minus 11 is 5. So at best, you're going to get 5 digits. And here we were starting to see this thing die at about 3 digits. So another thing, so you immediately look for catastrophic cancellation, and it'll tell you won't be able to do any better. Then another thing is to just, whenever you solve a linear system, check the norm of the residual. And you'll learn whether round-off is causing problems. Because the linear algebra library will try and solve it the best it can, but up to round-off. And it can't do any better. Like here, the entries in V times C are going to, the cancellation occurs when V hits C. Remember, C is the solved vector. You're checking, basically AX minus B here. That's a vector. You're checking its norm, which by default is the 2 norm, so just summing the root mean square, if you like. And you can see the norm of the residual is 10 to the minus 4. That's also, about 12 digits worse than it should be. Conclusion, right? There was some different factors going on here. Firstly, this polynomial seems to be doing a terrible job, but then and converging quite slowly, meaning as you increase n, the errors are not getting that much better. But then when you start getting n above 30, this catastrophic cancellation kills you anyway. So you literally can't get any better than about 3 digits. So the whole point now is to professionalize this, but it's kind of fun. This is teaching you how to debug, if you like. Okay, so we want to get errors down to close to machine precision. How do we do that? The very first thing to do is notice that we weren't working on the interval minus 1 to 1, which is the natural interval for polynomials. Here's the polynomials, or the monomials, right? The x to the k on minus 1, 1. You can see they're all sort of, they're not very linearly independent looking, but at least are scaled to have a size 1. And if you imagine going out to 5, then you're going to have 5 to the power 40, and that's a very large number, and that's why we were getting catastrophic cancellation. It's one reason. So what you should do is shift and scale. So you want to make it feel like the polynomials are seeing numbers from -1 to 1. Of course, so the best way to do that is to set, here's the center of your interval, 5 plus 1.1 over 2. Here's the scale, so the width, so the half width of your interval. And then just set a map, make a little map that takes input values x, subtracts them from the center, and divides by the scale. So that just maps the interval you want to -1, 1. Okay, and then when you construct this van der Waals matrix, you take the nodes that were in your physical interval, if you like, map them to the -1, 1 interval, solve as before. Let's put n is 40. Remember that we were trying to crank up the degree and the number of nodes. Well, now you get the entries of C are actually only 10 to the 4-ish in size. And remember that the entries of V now, because all of the nodes live in -1, 1, are within ±1. So that actually is telling you that, remember, we've got 11 digits of cancellation. You can only really get 4 or 5 digits of cancellation now. And in fact, you check the residual norm, and it's now down at 10 to the -11. And you've actually done something really useful, made the solution more stable. OK, so then you take your approximant, and don't forget, when you eval the poly, you've got to eval it on the shifted and scaled x, so that the eval poly sees the things that are on -1, 1. OK. So now n is 40, gets you just below 3 digits. Great. OK, it's a little better than before. The system, unfortunately, goes unstable when you start increasing n again. So what are we going to do? Now I will ask someone who knows to tell us what we've been doing wrong so far. Change the one? Change the sample points. Yes. Right. So now, so what's going on? There is a famous, so conclusion is we're going to use a different set of nodes. That polynomial interpolation through equispace nodes is a dangerous thing to do. You can do it. You just have to be careful. Here's a nice demo of a famous function from Runge like 120 years ago. Here's 32 nodes. Here's the function, 1 over 1 plus 9x squared. Here's the polynomial interpolant. It may as well be the exact polynomial interpolant through that. You don't even need to, well, and here's the error, right? So the error is of order 10 at the endpoints. It's actually good in the middle region and bad at the two end regions. And so it blows up. The exact interpolant is blowing up. This is not even a rounding error issue like we were dealing with on the previous page. You could do this in exact arithmetic. You could use big floats, do whatever you like. It'll still look exactly like this. So, and actually to get this to happen, the function, even though it's smooth and in fact analytic, needs to have nearby singularities. So there's some stuff to do with the complex plane. This function has poles. You can stick in x is plus or minus I over 3 in the complex plane, and that blows up. So even though it's smooth along the real line, it's the complex singularities, just like Taylor series, just like many things, are controlled by things that you might not have thought of off in the complex plane. So, OK, so the fix, the universal fix for this is to use Chebyshev nodes. So these are the mapped, they're clustered at the ends, and they're just given by sending the uniform grid through the cosine function. So if you like, you put uniform points on the semicircle and just project them down vertically. Now look at the error. It's 5, what is it? It's 4 or 5 digits. So you've gone from -1 digit to 4 or 5 digits just by changing the nodes. And we're actually, one thing I'll say that is these nodes are called Chebyshev nodes. Don't confuse them with Chebyshev polynomials. Chebyshev had a lot of things, invented a lot of things. We're actually still going to work in the monomial basis, meaning x to the k. Okay. Any questions? So how are we doing? So let's take these nodes, this new node set. I'm going to evaluate them on -1, 1. That's where the Chebyshev nodes naturally sit by just taking an equispace grid from 0 to pi and sending it through cosine. Okay, now we're going to evaluate the van der Waals matrix on those nodes. We're kind of working in t is the rescaled variable. So it's common to think x is your physical region where you want the function to live. T lives from -1 to 1. Okay, fill the van der Waals matrix. Evaluate the data. Notice you're sending the tj nodes through the shift and scale so that they're back where the original function should see them. And solve the linear system with 30 nodes. And look, you get 8-digit accuracy now. And the error is not blowing up at the ends in that sort of very dramatic fashion. It's kind of equidistributed. So, and if you now start varying n and redoing the experiment, so here we are plotting the worst error, so the L infinity, maximum error, whatever you want to call it, as a function of how many nodes you're going to fit. And you get something that looks at least exponential convergence, right? So it's on a linear n plot, it's dropping exponentially. And basically you hit 11 digits at n is 40, and that's getting to be acceptable now. Okay, so what's the theory for this? So, pretend we're not working on a computer. Just think about exact arithmetic using the interpolant, whatever polynomial. And this theory actually applies to any family of nodes with the Chebyshev density, which is this sort of clustering at the endpoints using the projection down from a semicircle onto the line density. So you can pick other node sets that kind of look the same, and you'll get the same results. The first result is that this is near optimal, meaning if p is any polynomial, not an interpolant, it doesn't match at nodes, just any polynomial, then the best you can do over the space of any polynomial of that degree is this, I've written as a intimidating looking definition, but that's just the best you could ever do with a polynomial of that degree. And up to a constant, a small constant, you get that same error. So that's a nice property of Chebyshev nodes. Another thing now is to think about this convergence. So how did this graph drop as n grew? And it's exponential, and you can even predict the rate. So this is rho is the exponential rate. How do you get rho? Well, you look at the interval -1 to 1. You look at the mapping, your function, right, mapped onto this standard interval -1 to 1. So this isn't the original f. It's, if you like, f acting on shifted and scaled t. But we could just transpose that f to the t plane and have a look at what it does. If there's a singularity, what you do is you say, here's a definition of an ellipse called a Bernstein ellipse of a parameter that's called rho traditionally, and rho defines the ellipse by rho plus 1 over rho being the major axis, rho minus 1 over rho being the minor axis, and then you say, how big can I grow that ellipse until it starts to touch the first place where the function becomes singular, is no longer analytic? Well, that rho then tells you the convergence rate of this interpolation at Chebyshev points. So if f has a nearby singularity, that causes a slow rate. Okay. If the function is not analytic, but maybe has some derivatives, you get algebraic convergence depending on how many derivatives it has. Like think of a function with a kink in it or something like that. You're not going to get this beautiful exponential error. You'll get something worse. So some of you may have noticed, Sorry, I just flashed it up. Did anyone notice what the original function was an approximation to? Function you shouldn't think about. Something that's obsessed pure mathematicians for hundreds of years, well, 150 years. All right, so yeah, so here it is again. F was the first million terms in this infinite series here, infinite sum, 1 over k to the x, which is the Riemann zeta function, written zeta of x, okay? And actually, if now you start looking up things about the Riemann zeta function, it has a pole at x is 1. Remember, remember the function went from 1.1 up to 5, and that's what we mapped to this standard interval. So 1 is right next to 1.1. So you actually have a pole. Well, you can see there was a pole. You go back to the original function, you can tell something bad is just about to happen. It turns out that's a pole at 1 if you were to sum the series correctly all the way out to infinity. And of course, there's plenty of ways of doing that that we're not going to discuss. So, okay, but you can take that known singularity location, use it to compute a row, and then predict the convergence rate. And that's rho to the minus n, and you get the red curve. And then you're a bit confused, as I was this weekend, because it actually does a lot better. But remember, it's just an upper bound on the convergence rate. It turns out that if you actually do the polynomial approximant for the true zeta function, it gives you the orange curves, which match the predicted convergence rate perfectly. So it turns out that the tail from 1,000,001 up to infinity is the thing that's actually capturing that pole, and the approximate, your expensive function did not capture that pole correctly, and it actually converged a lot better because it doesn't see a pole. Okay, well now I'm anthropomorphizing things, but okay, any questions about that? This is most of the things you need to know about Chebyshev nodes.
I have a question.
Pilar.
So here, would you say that n equals 35 for the approximate function is the best? Like where your error starts?
Well,
or
it's
which
been
n should I choose?
whatever you can, the smallest you can get away with in your application, right?
That gives me the best number.
Well, yeah, I mean, you may not want it. Okay, I mean, the evaluations are so fast that you would have, it wouldn't matter. Like, maybe it would take 1 nanosecond to evaluate it at this many terms and 2 nanoseconds at this many terms. So would that matter? I don't know. You may as well just converge the thing down so you don't have to worry about it. But in fact, you don't want to go much higher than the n shown here because, well, yeah, this whole, yeah, I was going to make this point anyway, but like solving with a monomial coefficient like this and evaluating that is really not stable beyond n is 40. So yeah, but it's kind of up to you to adjust the dials until you don't have to think about that error anymore. Okay, anything else? All right, good. So this idea is maybe the biggest single idea in numerical computing. Namely, we're trying to deal with continuous objects, functions. We're trying to handle them in computers. And by a computer, I mean it could be a human, a piece of mechanics, a mechanical object that was you hand crank on the desk, or an electronic computer. They can all only handle discrete numbers. So this is the way to handle functions using discrete numbers. Okay, as I was saying to Pilar, okay, you should not really handle this monomial form at n is 40. It's a bit large. It's certainly the upper limit. But this whole thing I've just presented, solving for monomial coefficients by solving the van der Waals system, is really easy. It's really fast, and it's accurate for n is up to about 30, sort of guaranteed. So this I learned from Johan Helsing, who was a postdoc with Leslie many years ago, who's a master of boundary integral methods. But interestingly, it was only recently proven by Kirill Sirk and Shen, his student, up in Toronto 3 years ago. I say 3 years ago because it took 3 years to get through review, I think because people found it such a shocking result. You won't find this in textbooks. The textbooks never say solve for the monomial coefficients by inverting an exponentially ill-conditioned matrix, which is what we've just been doing the whole time. But it's actually stable, and they've proven it. So that's why I'm teaching you this way to do it. It's not standard. OK. So now some other sort of notes. How can you go beyond this? Let's say you want to you know the targets in advance, the new points you're going to evaluate, and you fix the nodes, but you actually don't want to fix the data. Then you can pre-compute a matrix that maps you from it's going to map you from the nodes to the targets, and then you can send in new fj values or new vectors as you like, and it will then do this sort of as fast as possible, meaning as fast as BLAST2 arithmetic allows, which is very fast, right? You can't really beat the evaluation speed of a matrix hitting a vector. So that would allow you to throw in new functions as long as they were all smooth, then sufficiently smooth, then it would work. OK. Other things you can do. You've got this interpolant now. You can differentiate it analytically. So just each term, ck, becomes you take the derivative of xk, it becomes k ck minus 1. So just now do eval poly on this guy, and you've computed the derivative. You can continue that. And you may say, well, I know how to compute the derivative already. I just evaluate the function at 2 very nearby points and subtract and divide by h. OK. That involves catastrophic cancellation, what I just said, which is called finite differencing. This idea of building a global interpolant, high order, does not involve catastrophic cancellation because the nodes are not that close to each other. So at least it involves just the amount of instability that differentiation would induce anyway. So you can ask me. I can be more precise about that if you want. OK, but here's another thing. You can integrate it. Just take the polynomial interpolant, integrate it term by term, and now you've done quadrature on that function. So you can derive the rules that way, so on. OK. You can also evaluate this interpolant outside, but near the domain that you solved it on. That's called extrapolation. I should have drawn some pictures for that, but just imagine walking off the domain. This is exponentially sensitive to the data as you try and go further away, and you try and grow the degree, so you try and get more accuracy. So you can't get around from that. You're trying to do something ill-posed, but it can still be a useful tool. And many of us use it. David is a big user of this and has written here we are, a paper back in 2019 that shows that this idea of function extension is very useful for PDEs. And so what you can do is take the function and extend it along in radial direction, all just outside your domain, even in a 2D domain. And then you want to roll this function off. And I thought I was going to have time to describe smoothly rolling off and partitioning functions, but that's not. I don't have time for that. You can ask me how to do that. And then you roll it off to 0, and that makes a nice big smooth function that's smooth everywhere. And then you can send that into an FFT. And FFTs, like smooth functions, you can then solve PDEs quickly using the FFT. So, OK, a nice result is that so Charlie Epstein and Shidong Jiang, who are both in the room, developed their way to do function extension, which is beautiful in that it involves checking what's the smallest weights that you can use and what set of nodes gives that. And it turns out that putting Chebyshev nodes in the interval that you're going to measure the function is exactly the right thing to do if you want to do extension as well. So, OK. So this has all been pretty basic technology, evaluating the monomial. And it'll only get you so far. So, and in fact, you won't find it, as I said. So the classical things you'll find, although I don't know what the word classical means. This was really a hot topic in like 20 years ago when Barnett and Trefethen wrote a nice paper explaining that the right way to do polynomial interpolation is with this, what's called barycentric Lagrange formula. This, you take your nodes, right, are the xj's. You first, they can be any nodes in an interval. You take n squared time to compute these weights, this funny 1 over product of some stuff, okay? And then you do this weird sum with some what look like poles on the top and then with some other poles on the bottom. And miraculously, this whole formula turns out to be the polynomial, the unique polynomial that goes through the data. It's very strange, but basically there's cancellation in the top and the bottom, and that means you get exactly the right answer to machine precision as you hit each of the points. So it's a very useful and more accurate interpolant way to evaluate the interpolant than what we did. But just remember, you're evaluating the same interpolating polynomial, just with slightly lower machine error. So you're going to get the same convergence rate. If you were n is 10 and and it hadn't converged very well yet, that would still be true for this. But it's a more stable way to evaluate. Okay. And so, oh, by the way, so let's say you had n is 1,000 now. You could evaluate it stably with this formula. Be a little annoying because of the n squared cost, but you could. Okay. And if you want to go to really huge n, there's a whole technology where if you're using Chebyshev nodes, and now you're going to switch to Chebyshev polynomials, which is a different basis than the one that we've used up till now. The trick here is that this cos theta, you can think of this -1 to 1 in t is going around the unit circle in theta. So you can do everything using periodic FFTs and spectral methods. So again, it's evaluating the same polynomial in another way. So if you put it at n is 10, you'll get exactly the same error as before. So Trefethen sort of pioneered this, and it became a well-used, mostly one-dimensional interpolation and function handling package called ChebFun. So, okay, and if f itself is periodic, like the interval wraps around, then you just use a Fourier series. And I've had a bunch of notes, actually, from the first FWAM 2019 on that. So, okay. So, but this is not the only way to do things. How long have we got? Yeah, this is good. So we're still going to think about one dimension, but there's a lot of other ways that you should know about how to create a surrogate function. So the next trick is that everything we've done so far has been forcing the whole interval of the function that you want to be represented by one polynomial. That's called global interpolation. So the next good idea is to break that up into pieces and use a fixed degree, so not excessive degree, like 10 or 16 or something on each of those panels. And we can call the intervals panels. And this can be a lot more efficient than trying to handle everything globally. And the idea of this is the function has something wiggly or spiky happening. You just choose small enough panels around that area, and you'll get it accurately. So here's a different function that sort of has a similar flavor, right? It's got something oscillatory and near singular happening over here on the left side. It's very smooth out on the right side. You want to interpolate this. And the new idea here is the user gives you, or you are the user, you choose how many digits you want. We call that the tolerance. And then what happens is your code or somebody else's code starts trying to apply a global interpolant to this function. And let's say it says, OK, I've tried n equals 8. I've tried n equals 16. It's just not working. So I'm going to break the interval up into smaller intervals and then keep breaking them up until you get the error you want. So if you do that, then like you can see one big panel or one big subinterval is enough to capture the function out here. But it decided to split this into a smaller panel, and then these panels all got subdivided an awful lot. And here are all of the nodes that it ended up using. There are Chebyshev nodes on each of these panels. So it's quite easy to write a code for that, but you may not want to because you have to debug it. Then the logic has to work and stuff. Yes. Yeah.
So the first method you described won't work on that, right?
It won't work directly on this function because it's too wiggly over here.
Right. So
Meaning,
what
like,
can you describe what functions it will work on?
Something that is sufficiently smooth in the whole interval you're going to do the one panel on. And I actually chose one that was, that function right at the beginning. That's sort of pushing it, right? So that gives you an intuitive sense. Look, there's a singularity really near the endpoint here. That's actually not a great candidate for global interpolation. And we had to squeeze it quite high to go to like n is 40 to actually get that to work.
So you're assuming something about everything being bounded, including the different.
Yeah, it's to do with derivative. You could write it in terms of bounds on the derivatives and things like that.
Okay.
There's a whole bunch of theorems about that.
Thanks.
But yes, it's about smoothness. And now you could use this Chebyshev stuff, crank up n to as high as you want, and ChebFun actually spends a lot of time showing off very horrible-looking functions that can all be done by a single global interpolant. I don't think that's the right way to do it. I think the best thing to do is to break it up like this and use like degree 16 on each, and then optimize your evaluators on each for that. So, okay. This idea of adaptively breaking up the interval is very commonly found in good quadrature codes that you can find in many languages. Sometimes they're called quad GK, because Gauss-Kronrod is a particular set of rules for these nodes, but we don't have to worry about that. Weirdly, in the interpolation side, there's not much adaptive code for interpolation. So, we're kind of, in other words, a lot of the ones I know about, and maybe that's just that my extremely small worldview, but I don't think so, are friends. So Biopsy does 1D up to, I think it's now arbitrary D, but you should use it in relatively low D by Robert Blackwell, and Marco Barboni is helping on the evaluators for this. So this is a adaptive splitting approximator like this that you will have. It has interfaces from different languages, so that's sort of in development. Please use that and give feedback to Rob. And then another Julia-specific one is H-Cheb-interp, where H stands for H refinement, which is what making these panels smaller is sometimes called. And so this is by our collaborator Lorenzo van Munoz, who's Stephen Johnson's grad student at MIT, based on stuff that Jason Kay and I and him all came up with for applications in band structure. So, okay, ChebFun I mentioned already. Okay, so there is a bit of a need for better or more widely used code on this. So, because, right, here I'm going to point out some other interpolation methods. That is, if you actually go out to the Wild West of software out there and look for interpolation libraries, you will find essentially what is on this page, which is completely distinct from, or almost completely from what I just said. Okay, so what they all implement is piecewise linear. Okay, connect the dots between the data. Okay, people actually release libraries for this, but that's because maybe they have a very fast way of figuring out in which interval your point is, things like this, right? Now, how accurate is that? Well, if n is the number of nodes here, right, it's the gap between the function and the straight line, and the spacing h is 1 over n, and this will go like h squared. So you basically get 1 over n squared accuracy here. If you want to get 12-digit accuracy on a typical function of a sort of typical wiggliness, you will need 1 million points. That's not great. That's an awful lot of data to store compared to what we just did to get 12-digit accuracy. So Okay. By the way, I should say that all of these methods I'm going to show are using a different interpolant between every pair of every neighboring pair of nodes. That's a different idea from what we just were doing. Okay. Local Lagrange is kind of the higher order version of piecewise linear, and it says wherever you are, whichever interval you're in between nodes, look up the nearest p nodes and construct the local unique degree p minus 1 polynomial through those nodes, and then use that just for this interval that you're in. So if you move to the next interval, it's going to use a different interpolant, and so on. So this uses polynomial interpolation we've just been doing. It gets you algebraic convergence at order p, and p can be made quite high, like 10 or something. So that's good. It's discontinuous, though, so if you actually zoom in and look, the function will have, your f tilde will have little jumps. That isn't a problem usually. It's still accurate. Okay, and then, again, very popular is piecewise cubic splines. So you take these nodes, and you have to sort of set up a tridiagonal system that says, how can I get cubic polynomials to match up so that their values, derivatives, and second derivatives all match up at all of the nodes? And that gets you fourth order accurate because it's a cubic polynomial. Okay, why are these popular? There's tons of software for piecewise linear and piecewise cubic splines. Go out there, but actually there's not tons of software. I don't know of any software that implements local Lagrange in a usable way. So that's another software lacuna that needs to be fixed. Why is doing things this way using intervals between nodes popular? It's generally stable under noise compared to some of what we just did. It works for arbitrary nodes. Remember, in the data fitting situation, the nodes are thrown to you, and you have to deal with whatever they are. And everything is ON, so it's cheap. So I think that's why those are popular. But again, they are distinct from this adaptive high-order idea. Okay. I'm trying to give you a landscape of everything that's out there. That's the main goal. So all of this is not a new idea, especially when you deal with regular grids. So I'm going to show you the complete history of lookup tables. Here's Napier's invention of the logarithm in 1614. These are tables of logs that you can then use to compute things like multiply numbers together cheaply. Here's Abramowitz and Stegun, which is a special functions book that you all probably know and love. And these are some spherical Bessel functions. They're all tabulated on regular grids. What are you supposed to do with those numbers? Well, firstly, they all died out because of hand calculators coming in the 80s. But actually, there's a beautiful chapter, which no one ever reads, at the end of Abramowitz and Stegun by Davis and other people that tells you how to interpolate off these tables. And in fact, they say piecewise linear, drawing straight lines, is acceptable, if you want 5 digits or something. And then they explain how to do local Lagrange there. There's lookup tables for local Lagrange that are like the lookup table for how to apply the lookup table. So, okay. So this thing that we showed with these adaptive panels is a modern sort of lookup table in a different style from these. So, but all of this idea of lookup tables is essential if you want to do things very fast. So down at the inner loop where you're evaluating square root or sine or some function of your own needs fast, these all remain essential. Okay, so now I'm going to show you a fun thing that is sort of less routine, but it's shockingly accurate, so it's kind of fun. That you can find nearby singularities of functions, and this comes up in our research with Jason Kay and others at CCQ. Remember, we're back to like one node with one interval with some nodes on it. Or you can think of this as a set in the complex plane. We're going to choose a completely different interpolant now, which is a polynomial over another polynomial. So each of them at degree k minus 1. If this is true, then it should approximately hold that p minus f, the data hitting q, at each of the nodes is 0. Okay. Well, that looks like you could write out the linear system for it. So remember, p is the sum of some ck's and has a van der Waals matrix. So each row of this linear system now, take the first row, right? It's imposing at the first node that some coefficients hitting these monomials minus f1 hitting these monomials is 0. And then each row imposes that at a node. So what you're actually, if you look at this linear system, the right-hand side is 0. So it's a homogeneous system, and you're trying to find a vector C that is in the null space of this matrix on the left. So, and the vector C contains the first k entries are the coefficients for the p polynomial, and the second k entries are the coefficients for the q polynomial. So the way to do this numerically is now just take the SVD of this stacked van der Waals pair, extract the last right singular vector, pull out the coefficients of p and q, and this is a simplified version of something called robust PAD-A that was invented in like about 10 years ago. Okay, and then you can look at p and q and interpret them. This is an interpretable model, if you like, in the language of yesterday. You can say the zeros of q tell you where the poles of f are. That's the important thing. So it's quite a useful way to sniff out nearby singularities in a function, just given it's a set of values. Yeah, it's very cute. Now, there's fancier ways to do this, but anyway. So let's demo this. Again, a little Julia code. I'm actually going to go back to the exact Riemann zeta function, because that's the thing that has an actual pole nearby. Let's pretend we don't know where it is, or we don't know what the function looks like. So, okay, so you pick a degree, you pick a number of nodes, you set up some Chebyshev nodes. Here's your costly function, which is the zeta function. Set up the van der Waals, stack the van der Waals with minus the data. That's your stacked matrix. Take the SVD, extract from the last singular vector the coefficients of p and the coefficients of q, and now rescale them, shift and scale back to the physical plane, x plane, and and then print out some of the answers. Well, I didn't print out the 7-element vector that you get for q, but one of them is 0.0999. All right. In other words, it's finding that pole to 14 digits. So, and this is with a degree 8 and 20 nodes. So it's a fun thing to do then. Oh, and you can check that the error of the interpolant, of the rational interpolant in that interval is 12, 13 digits. And this is only 20 nodes and a degree 8. So it's a much more efficient way to extract that, to like represent that function in that interval. You're using half, if you go back to the zeta function, remember the orange convergence plot actually was pretty slow. That only got 2 digits if you used a total degree of 16, which would be the same as the same amount of information you're using here. So it's a very efficient way to approximate functions with poles, the meromorphic functions. Here are the nodes. And now I'm just plotting the zeros of the roots of q, which are the poles. So it puts that x right next to the end, which is where the true zeta has a pole at 1. And then you can look at other things. Look at the zeros. There's a 0 here at very close to -2, and another one, well, those two should be the one at -4. Those are called the trivial zeros. And in fact, there's a 0 up here at one of the famous zeros, at a half plus or minus some imaginary numbers. These orange ones are actually quite close to that. But the thing isn't completely routine, because look, here's a pole and a 0 right on top of each other. That creates something that you don't want to deal with. So you sometimes have to filter these out by hand or try and automate it. So all I'll say about this is it's a nonlinear method, right? If you do it for 2 functions and add them up, you won't get the same as if you do it for the sum. It requires some human intervention often, And then there's, may have heard of this AAA method that Trefethen has been, and collaborators have been promoting as a sort of successor to this. I have not needed this one. I'm very happy with using robust, just small SVDs, are quite fast. So there's a quadratic variant too. Okay, noisy functions. Everything so far has been matching the zero noise. If it's noisy, you jump to statistics and optimization. You pick a model for the noise. You pick a model for the signal. You put them together to get a likelihood. You do regression, which returns the maximum likelihood estimate of the parameters, the unknown parameters. And for instance, you can still do that using your van der Waals solve if you just reduce the degree compared to the number of nodes. Or you could do Bayesian inference, which you pick a prior on the coefficients, apply Bayes formula, and then draw samples from the posterior on C. So, and then you can do, the main problem with all of this is that it's very hard to know what the noise model for a simulation is. Okay, summary for 1D function approximation. I think I'll skip this because I've said it all quite a lot, but this is, I kind of put a list of bullet points of what we just did. Use Chebyshev, don't go to too high degree, otherwise break up your intervals adaptively if you can. If you can't choose the nodes, use this local Lagrange, and then other stuff. And then we'll talk a little bit. I have like 2 slides on higher dimension. So lowish dimensions, 2 to 5 or something. You can use tensor products of everything I just talked about. You can either take tensor products of regular grids, do like bicubic interpolation, or do an FFT off the regular grid using the non-uniform FFT. You can do adaptive boxes where each is a product Chebyshev, and you pay the curse of dimensionality, right? Because these are dense boxes in filling the dimensionality. If you can't choose the nodes and you've got randomly scattered data, things get a lot more fun. And I like showing this picture from Google Terrain, which I found. You can see there are point samples of the height of the terrain that have been used in some pretty ghastly like spatial regression algorithm to interpolate the heights of these mountains in between those points. If you went to this region of the world, you would not see little kernel spikes like this coming out of the ground. And especially you wouldn't see a transition along this perfectly horizontal line to another region where everything is built from linear interpolants, which is what the data must have changed that they had from the satellite or something here. Okay, you get to see like how messy it is, but that's kind of the real world. So if you don't choose the nodes, you can do the multivariate analog of local Lagrange. Just pick the few nearby nodes, fit a polynomial, and just do that wherever you need it. You can get into trouble because uniqueness is not the same for multivariate polynomials. You can do radial basis functions, which is just using a different basis set than a polynomial. And you can write a global Fourier series, like in MRI, and use a least squares solve, which you can iterate on using non-uniform FFTs. And if you're in the noisy world, which I mentioned, like the statistics inference world, you can use Gaussian process regression, which requires you to commit to a kernel covariance and a noise level. And I will plug that we have developed an equispace Fourier Gaussian process method. This is with Philip Greengard in CCM and Manas and myself. That's good for low dimensions and is starting to be used by people in CCA and in Stanford. So there's that. And then final slide, high dimensions, very high dimensions. It's worth a try in less than 100 dimensions to do these things called sparse grids. I'm not an advocate for them. I have never tried them. They look like sort of pared down versions of Chebyshev product Chebyshev grids, where the paring down only occurs, where some of the lines are dense and then others are less dense and so on. And they can even do adaptive versions of these. The good thing is the number of nodes instead of the n to the d cursive dimensionality, which is exponential in d, it's d to the k. And k is something small, and that's actually OK. So, but other people say you can pick random nodes, and it's even better. So, and then I'm way out of my depth for high dimension. Tensor train, if your dimensions sort of talk to each other, there's a natural ordering on dimensions. Tensor train is worth trying. And then there's neural networks, and just talk to other people about all of that. But the main point about high dimensions is the assumption on the function is going to be so strong because you can barely sample it very much. It's mostly gaps that really it's all application dependent, and it's to do with what assumption you put on the function. And these sparse grids even place assumptions on the functions that they sort of, if they have lots of derivatives, if they're high degree in certain dimensions, then that uses up all of the degree, and you can't vary in the other dimensions. So they have to have some kind of approximate separability. And that's it, conclusions. So I was going to draw a big decision tree, which starts with what's your dimension, and then it would be, are you going to do low noise or high noise? Or are the nodes given to you, or do you get to choose the nodes? But I think I've taken you through some of those questions. So including how to write 1D codes that are reasonably useful. Always go to high order. And then some ideas for 2D and high dimension. So I'll just leave you with those. Thanks a lot.